In this video, we're going to talk about powers of group elements. Okay, so let's start by letting G be a group. And again, I'm going to speak as though the operation on G is multiplication, even though the operation can really be whatever we want. I'm just saying that if I want to combine two elements, A and B, I'm going to write that as just AB, as though I'm multiplying things. Okay, so we're going to let G be a group, and let's fix one element of G, call it A. Okay. Now, here's something that I can do. Here's a little game that I can play with A. I can combine A with itself several times. And because my operation is associative, it doesn't matter when I write this whether I mean this or whether I mean this. I could mean either one of these and it'd be the same thing because these two expressions have to be equal by associativity. Or I can multiply even more A's. I could multiply 4 A's or maybe even 5 A's. And that would be a well-defined product. It wouldn't depend upon where I would place parentheses. So even though multiplication is really strictly a binary operation, we can only multiply two things at a time, I can combine all 5 of these together by picking some order in which to combine things. Like I could combine these first, and then combine with this, and then combine that result with this, and so on. So anyway, we're going to invent a more compact name and notation for this because more often than you might imagine, we actually do combine the same group element with itself multiple times. All right, so that's what exponents are for. We're going to develop the language of exponents for group theory. And it's not too different from what you're already familiar with. So we're going to start with this definition here. So I'm going to start by saying let G be a group. Let G be a group. And let A be an element of G. And I'm going to say we define. Well, first of all, we define A to the 0 power to be the identity element. This is the group identity. And again, Gaulian uses E for this. I often use the numeral 1, just because it reminds me that it's something that I can multiply by anything and it doesn't change what I'm multiplying by. Okay, so that's A to the 0. That's our definition of A to the 0. And second of all, if K is a positive integer, then I define A to the K to equal A times A to the K minus 1. So in other words, if I want to know, for example, what A to the 5th is, then I take A to 1 smaller power, so A to the 4th, and then multiply by another A. This is what's called a recursive definition. This actually isn't the way that Gaulian starts on this. This is a recursive definition. But this is kind of a formal way that we define what A to the K is when K is a positive integer. Intuitively, and this is more like the definition given in Gaulian, intuitively, when we say A to the K, where K is a positive integer, we mean A to the K is a product of several copies of A. How many copies? K copies. All right, so that's what A to the K means. All right, but now here's the twist. In a group, because every element has an inverse, I can also talk about negative exponents. And that's the next part of my definition. So if K is a negative integer, then I define A to the K, which remember that's a negative power of A to the K equals A inverse to the absolute value of K power. Meaning, for example, if I wish to define A to the negative 5th, then I take the inverse of A and raise that to the 5th power. And that's defined by part 2. I've already defined what positive exponents mean for any group element. And A inverse is a perfectly good group element. Now, under this definition, here are some things that I know. So here are some things that are true. I'm going to zoom out so I have a little bit more room to work while still seeing the definition of exponents on my screen. There we go. So here are some things that I can say. First of all, if I have a product, so if A is in G and M and N are integers, then a to the m plus n is equal to a to the m times a to the n. And one way that we can verify that sort of informally, so I wouldn't call this a formal proof, but if m and n are positive integers, then I can think of a to the m plus n as a product of a bunch of copies of a total of m plus n copies. And then I can think of this other product as being a product of some copies of A, m of them, times some more copies of A, n of them. And because multiplication is associative, I can regroup this expression on the right and recombine these so that what I really see altogether is a total of m plus n copies, which is the same thing I have on the left. So that's why that rule is true. I don't know if you ever thought about that in high school algebra when you learned the same rule there in that setting, but that's why this rule works, at least for positive integers. For negative integers, the proof is a little bit more intricate, and this is why I'm not doing this really in full in this video, is that it requires some casework, and to do this formally uses induction. But you can actually prove this rule in the case where m is negative, or where n is negative, or where m and n are both negative, and that might be a fun puzzle to think about. We just won't do it in this video. Okay, here's another rule that I know is true. Number 2. If A is a group element, and m and n are integers, then here's something else I know. A raised to the mth power raised to the nth power is equal to a to the m times n, where that exponent is the integer product of m and n. And again, I can reason this out just using my intuition about repeated factors of A. So let's try that out here. Okay, so what does this product mean? This product means I'm going to take the product of m copies of A. There we go, that's m copies. And raise that to the nth power. Well, what would that mean? That would mean that I'm taking m copies of A and multiplying that by itself n times. So that's going to be a bunch of these, dot, 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 and then let's put one last one there. Okay, so again, I've got m copies, m copies, m copies, and I'm doing this n times. Okay, but then how many A's do I have altogether? Well, I have n groups of m factors each. So the total number there, and again, I can reassociate these without any trouble, the total is m times n copies. So that's why this is equal on the right to a to the m times n. Again, doing this when m or n is negative is a little bit, it requires a little bit more thinking. We have to think about what negative exponents mean. So we're taking copies of the inverse of a rather than a itself. But actually, this one works out pretty nicely, even when m and n are negative integers. Okay, so those are two rules that we know. Now here's something that is not true. So I'll put this in a different color, and I'll put not true. Fake news. If A is in G, and B is in G, and n is an integer, then A times B to the n is equivalent to A to the n times B to the n. Okay, now why is that not true? Well, I'm going to give an argument, rather than giving an example of when this is not true, which I could do, and I might suggest a place where you can find one in just a minute. Instead, I'm going to sort of argue by talking about what would be true if I knew that this were true. So if this were true, then I could always do this. So I could always do the following thing. Well, I could say that a times b squared is equal to a squared b squared. And then that would mean that if I interpret the product on the left literally, meaning I'm taking the group element AB and multiplying it twice, that's equal to a squared times b squared. And again, because group multiplication is associative, I can just rewrite this without the parentheses. AB equals a squared b squared. Okay, now here's where the fun starts. I'm going to rewrite the right side as just AABB, because there's no problem with doing that. I can repeat factors if I want to. Okay, but now look. You remember that I have a left cancellation law and a right cancellation law. So by left cancellation, I can cancel the a on the left, and by right cancellation, I can cancel the b on the right. And then what am I left with? I'm left with BA equals AB. And this would be true for all elements A and B of any group, because I made this argument in total generality without assuming anything about the group. But if this is true, if this is always true for all A and B, then G is abelian, because that's exactly the statement of what it means for the operation to be commutative. And, well, not all groups are abelian. We've seen an example of one that isn't. And that's where you can find a concrete example of where this would fail. So just take any elements A and B that don't commute, and you'll see that AB squared is not the same as A squared B squared. So that is something that we can't do. So it's kind of interesting to reflect on how we have some laws of exponents that we've sort of accepted for a long time without questioning, like addition of exponents and multiplication of exponents. But it turns out that some of those work in broader algebraic contexts and some just don't. Some of them fail. So that's kind of interesting to think about. And in order to think about these things carefully, we have to remember that our operation is not commutative, so we can't just move factors past each other.